Numerical integration. Let's start with an example. Say we want to find an integral from 2 1 over x dx. We know how to do it exactly using the fundamental theorem of calculus, but let's try to do it numerically. So we'll do the following. So taking from 1 to 2, we're going to choose n, which is number of subintervals. So in our case, let's choose n to be equals to 4. Then we calculate what's delta x, which is length of each subinterval. So length over a whole interval is going to be 2 minus 1 divided by 4 subintervals. So we're going to get 1/4. We are getting 1/4, 0.25. Now, if I mark these points in the interval from 1 to 2, I'm going to get 4 subintervals. And my endpoints are going to be 1.25, 1.5, 1.75. If I go by 0.25 from left to right. Now, if I want to calculate left sum approximation, so left hand sum or left hand approximation is n equals to 4. Instead of writing every time or saying every time left hand approximation if n equals to 4, I'm going to write down just L4. So in our case, it's going to be equal to, so in our case, L4 is going to be equal to, so for each interval, we're going to go by left point. So for first, we're going to calculate what's happening at 1. So we'll calculate f of 1. Then we're going to multiply it by delta x. The second interval, we're going to choose left point, so we calculate f of 1.25. We're going to calculate by delta x plus the next interval 1.5 times delta x plus f of 1.75 times delta x. So recall what that represents. So you recall what's the situation. So recall what L4 represents. So we have interval from 1 to 2. And we divided that interval into 4 subintervals. Then we picked left point on the first interval. We measured F1. Then we multiplied F1 by delta x, which is the width of that rectangle, and to get the following area of that rectangle. Then we calculate f1.25. We measure the height, multiply by width, which is delta x, to get the area of the next rectangle, and the next. So area of these 4 rectangles is L4. So that is our approximation to the integral. So L4 is our approximation to the integral. So you clearly see from that picture, actual value of integral is going to be smaller. So let's do actual calculations. 4 is going to be equal. Remember that our function is 1 over x. So we're going to get 1 over 1 times delta x, which is 0.25, plus 1 over 1.25 times 0.25, plus 1 divided by 1.5 divided by 0.25, plus 1 divided by 1.75 multiplied by 0.25. So we do the calculations and define what L4 is. So we calculate L4. Let's say we approximate our answer to 4 decimal places. So we're going to get 0.759. In a similar fashion, as we did left hand approximation, we can do right hand approximation. So what we're going to be doing is for each interval which we have here, we're going to be choosing now right point. So we're going to be choosing 1.25, we're going to be choosing 1.5, 1.75, and 2 to measure value of function. And the same fashion as we did before, we're going to multiply each value by delta x to get the area of the corresponding rectangles, and then we're going to add. So let's do the calculations for right hand sum approximation. So R4, that is the right and equals to 4. So we're going to get, so we're going by right points. So we're going to get 1.5 times x 1.5 times delta x plus f 1.75 times delta x plus f of 2 times delta x. If you want to see the geometric interpretation, if you want to see the right hand approximation on the graph, then it's going to look like this. So the first interval, we're going to put right point with the measure height multiplied by delta x. Second interval, pick right point, draw the rectangle multiplied by delta x, measure height multiplied by delta x, measure height multiplied by delta x. So those green rectangles in this case are going to be right hand approximation, and they will be underestimate of our picture. So let's do actual calculations. So R4 is going to be 1 divided by 1.25 times 2.25 plus 1 divided by 1.5 times 0.25 plus 1 divided by 1.75 multiplied by 0.25 plus 1 divided by 2 multiplied by 0.5, which approximately equal to, we're going to approximate to 4 decimal places, 0.6345. Let's recall what our actual integral is. Our actual integral is 1 to 2, 1 over x dx. We can calculate it by doing fundamental theorem of calculus. So we're going to get ln of x 1 to 2. So we're going to get ln of 2 minus 1. So we choose ln of 2, which is approximately equal to 0.6931, which is 0.639. That is the exact answer. So we can calculate errors. Error in L4, we're going to call it error in L4 is going to be equal. Actually, I'm going to be calculating only marginal error. So that equals to 0.7595 minus 0.6931. So our approximation is 0.7595 minus actual value. So it's going to be equal to so the answer is going to be up to 4 decimals, 0.0664. We will calculate error right hand sum, error in right hand sum 4. Actually calculate only its magnitude, so that's going to be equal to 0.6345 minus 0.6931, which is approximately 0.0586. So error in right hand sum is going to be 0.0586 and left 0.0664, which are about on the same magnitude. Now, if you want to get better approximation, what we can do is we can take the average. So we take average of right hand sum and left hand sum, and so I'm going to add them up, divide them two, and we're going to call that the trapezoid approximation. So we're going to be using letter T of 4 notation. So let's calculate what is going to be trapezoid approximation. Trapezoid approximation is going to be average of left, and if you recall that for left we get 0.7595. For right, we get 0.6345. And we take the average, so we divide that by 2. So again, because all our approximations to 4 decimals, so we're going to get, in this case, 0.6970. And the error in T4, it's going to be, we're going to be calculating only its magnitude, 0.6970 minus 0.6931, which is 0.0039. So error for trapezoidal is 0.0039, and if you consider it with errors which we obtained earlier for the left approximation and the right-hand approximation, then you definitely see that trapezoidal is much more accurate. Recall what we started with. Recall what we started with. We started from interval 1 to 2, and we divided it into 4 subintervals. Then for each subinterval, we're using the value of function to predict the height of our rectangle. For left approximation, we're using left points. For right approximation, we're using right points. But if you want to get the better approximation, instead of choosing the left or right, we probably should be picking midpoints. So we should be picking midpoints. So that is our next goal. So we'll try to do midpoint approximation. If n equals to 4. So let's do the calculations. So I'm going to be using n4 to denote that approximation. So firstly, I have to find those midpoints. So we recall that we have our points 1, 1.25, 1.5, 1.75, and point in between are going to be 1.125, 1.375, 1.625, and 1.875. So we got our midpoints. So we're ready to write down expression for M4. Expression for M4 is going to be F midpoint first interval times delta x plus F midpoint next interval times delta x plus F of midpoint next interval times delta x plus F of midpoint of the last interval times delta x. So the geometrical interpretation, for midpoint is going to be for each interval we pick a midpoint, we measure the height, then we draw our rectangles. We pick midpoint, we calculate the height, we draw a rectangle, next, and the next. From that picture, you clearly see that midpoint is supposed to be better than left or right hand sum approximations. Let's do actual calculations. Let's do actual calculations. We recall that our function is 1 over. You recall that our function is 1 over x, so we're going to get 1 over 1.125 delta x is 0.25 plus 1 divided by 1.375 times delta x plus 1 divided by 0.625 multiplied by delta x plus 1 divided by 1.875 delta x, which is 0.25. And we run our calculations. So we do the calculations. We round our answer to 4 decimals and we're going to put 0.6912. Recall that the actual value going to come from 1 to 2, 1 over x dx. We calculated somewhere here. So actual value is 0.6931. So with the error in M4, magnitude of it is going to be 0.6912 minus 0.6931. So it's going to be equal to 0.0019. Very small error. Very small error. So let's recall that error in trapezoid 4 is approximately 0.0039. Error in midpoint approximation is 0.0019. If you look at these numbers, then both trapezoid and midpoint are very accurate, and we can build up on that. We can take weight sum between trapezoid and midpoint and get even better answer. So that's what we're going to be doing next. So that is so-called the Simpson's approximation. So in this case, we're going to be calling it with 2 times 4. We're going to be calling it with 2 times 4 because when we do this combination between trapezoid and midpoint, the number of interval actually is going to be more than 4. We started with 4. We also get our midpoint intervals. So if you look for the total number of intervals we're dealing with, it's going to be 8. So that's why it's often going to be called 2 times 4, or Simpson approximation with 8 n equals to 8. So Simpson of 2 times 4 is going to be equal to, so we want to combine trapezoid 4, we want to combine midpoint with 4 subintervals. If you look at what we got for errors in trapezoid and in midpoint, if you look what kind of errors we got for trapezoid and for midpoint, then you notice that midpoint is twice as accurate as trapezoid because error was approximately 0.0019, which was half of error in trapezoid, which was 0.039. So we don't want to take T4 plus M4. We want to take 2 of midpoints and 1 of trapezoid. We want to add them up, but to keep average to be the same, so we're going to divide by 3 because we took 2 midpoint, 1 trapezoid, so we're going to end up dividing by 3. So if we do that, we're going to get over 3. You recall that midpoint is 0.06912. You recall that trapezoid is 0.6970. So then we're going to get Simpson approximation of 2 times 4 is approximately equal to Simpson approximation of 2 times 4 is going to be up to 4 decimals, 0.6931. We call that exact value is 0.6931 up to 4 decimals. So we notice, so you recall that exact value is 0.639. So we notice that Simpson with 2 times 4 is correct to 4 decimal places. So notice that Simpson rule is much more accurate than either midpoint or trapezoid.